So how do I make use of not knowing whether or not 283 is prime? How do I make use of this idea that if B divides A and B, then it's going to divide their difference to find the greatest common divisor? Out of those two numbers, take the bigger one divided by the smaller one. Give me a quotient and a remainder. What you got? I'm looking for the greatest common divisor of 2547 and 333, right? So whatever thing divides 2547 and 333, if it divides 333, it'll divide 7 times 333, right? Which means it'll divide the difference of these two things, which is 216. Whatever divides both 2547 and 333 also divides 216. So what if I do this process again using 216 and the smaller of my two numbers? Whatever divides 2547 and 333 will also divide 333 and 216. So give me a quotient or remainder. Whatever divides these two divides these two. So whatever divides those two divides these two. Do it again. We're going to do this over and over and over. There's got to be something that'll tell me to stop. Luke can't iterate forever. Why do I know this algorithm? Why do I know this algorithm will eventually halt? If I reach a number where I can't divide, I have a problem because my division algorithm works on all the integers. I don't have one remainder. It'll divide evenly. These numbers are getting smaller. At some point, that remainder number is going to be 0. What are my numbers here? 117 is something times 99 plus 99 is some number of 18s with something left over. And 18. Aha. Now, last time I checked, we said this both Wednesday and Monday, everything divides 0. So I know these numbers. What's the greatest common divisor of these two? Which means that divides these two, and 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 these two. The last non-zero remainder is my greatest common divisor. Son. I don't have to factor into primes. Now, I got lucky. We did actually factor these into primes. And notice that when I use the prime version, hey, 3 squared, greatest common divisor should be 9. It was. I don't care what the numbers are. You know how to divide. You can find a greatest common divisor. You don't have to know primes. You don't have to factor anything out. You just have to divide the quotient and remainder over and over and over. Try it again. Because this is a repeated call of the same function, this is a really, really easy recursive algorithm code. If my numbers are relatively prime, this will end with a greatest common divisor of 1. Both of these numbers are even, so the greatest common divisor has to be at least 2. And it turns out to be exactly 2. 1 times 414 plus 248. How many 248s fit here? 1 with 166 left over. Quotient remainder here. Quotient remainder here. Careful.
2 plus 2.
And then
41 and 0.
There's my greatest common divisor. I said this was an easy algorithm to code. Math button. Left column, third button down. Bunch of options at the top there, right? Those are options for numbers. Why the column heading is NUM. Rounding, integer part, fractional part, quotient remainder. Remember I said you take away the integer and just look at the fraction? Integer part of minimum, maximum. There's an arrow, that means there's more. But wait. Boop. There they are. See, I built them in, that's how easy they are. Should you use this? Damn straight you should to check your work. Greatest common divisor of 414 and 662. That was a lot faster than me. Well, of course it is, it's a computer. It would be interesting to try and figure out what the big O of this is. I'm sorry? The calculator won't do big O calculations for us on this one, sorry. I'd have to figure out how much I'm going down by each time, right? And that depends on the relative sizes of A and B. I need to know really the log of larger over smaller. But if I know that, then it's roughly log of. Or maybe it's square root of larger over smaller, because I have to know how much I go down by each time. That's going to be hard to calculate abstractly. This is not an easy algorithm to bound. Questions? Out of the three methods we have for finding greatest common divisor, this one's the most useful. We could just list all the divisors. We could do the prime factorization that requires me to know a lot of primes, or I could just repeatedly divide. And I'm good at it, especially with calculator. But even more so, this particular method was known all the way back in Euclid. This is called the Euclidean algorithm. In the mid 1700s, French mathematician by the name of Bézout he came along and said, you know what? If this is the greatest common divisor, 2 of those two numbers, then there should be a way to write 2 in terms of 414 and 662.
A1 something.
A comma B.
Okay, thank you.
If A and B are positive numbers, and D is their greatest common divisor, then there are 2 other integers, S and T. So you can write the greatest common divisor D as a combination of A and B, S times A plus T times B. So my question to you is, how the hell am I supposed to do that? How am I supposed to figure out how many multiples of 414 I need and how many multiples of 662 I need? One of those is going to have to be negative, right? You're going to have to take some number of multiples of 414 and subtract off some 662s, or maybe it's the other way around. Like subtract off the, oh crap. Bézout said, this isn't as hard as you think it is, because you have all the information you need written out in the Euclidean algorithm. What you need to do is take each of those equations, each of those equals that we wrote out, and solve them for the remainder. So, except for the last one, because the last one, the remainder was 0. Start with all of those, rewrite those equations so that the remainder is on one side. I'm going to start with the one with the arrow on it. 2 is 166 minus 2 times 82. Right? But up here, the 82 is the remainder. Let me number these so it's easier to keep track of. I rewrote number 4 and I got this. If I rewrite number 3, I get 82 is 248 minus 1 times 166, right? Let's stick this expression in here. I don't want to simplify. I want to regroup. I've got 248s, right? And those are being subtracted. How many 166s do I have? I got 3 of them. Because I got 1 out front and I got minus -2. Oh, okay, minus and 2. Okay, 3 of them. Now go back to equation 2. In equation 2, we would have the remainder being 166. 166 is 414 minus 1 times 248. I'm going to put this expression in there. And regroup. How many 414s? How many 248s? Whoa, be careful. That's a -3 minus another 2. That's -5 of them. Sign errors are going to be the death of me in this process. Go back to equation 1. In equation 1, the 248 is the remainder. So what am I going to do? I'm going to put this in for the 248. 2 is 3 times 414 minus 5 times 662 minus 414. And now I regroup again. How many 414s do I have? 3 of them here, then minus 5 is 5. 3 and 5 is 8. Minus 5 times 662. ST. Those two numbers, S and T, are called the Bézier coefficients. And since I am using the Euclidean algorithm to get these numbers, the process of doing both of these can be done together. First, you do it forwards, the Euclidean algorithm, then you do Bezout's part and extend the Euclidean algorithm to get these two numbers. So doing both of these together is called the extended Euclidean algorithm. I always think of them as two separate pieces, Euclid's part and Bezout's part, but that's me. $64,000 question. So what? Who cares? I'm sorry? That was the TV show, right? $64,000 premium? Oh, yeah. $64,000 question. So, why do I care? Ladies and gentlemen, those two numbers, the 8 and the 5 here, those will be the cryptographic keys to decrypt and encrypt in a public key cryptography system. I would love to tell you this is useless. But if I'm encrypting RSA encryption, I release a public key based on the Bezout coefficient of my private key. This is the reason secure socket layer works. That's what's keeping this in mind. I can also use this to prove my unique factorization theorem. That proof is in the textbook. I'm not going to go through it at this point, but this is the foundation of current cryptography. Questions? Realistically, the only difference between this and the RSA algorithm is the size of the number. I use the 3-digit number. RSA uses a 1024 bit number, or 330 some odd digits long. For both sides of the keys. If you're interested in this in more detail, the RSA algorithm is in our textbook, chapter 4, section 6. It will go through the complete behavior, but this is the foundational piece. And really, I consider one of these a modulus. I'm not just using 414 and 662. I'm doing my encryption mod 662 with a power of 414, which means I'm using that modular exponential algorithm we went through. So I'm trying to raise stuff, mod 662, raise it to the 414th power. And then I send that message out. Or you send that message to me, because that's my public key is 414. How do I decode it? I take your message and I raise it to the 8th. Because that will undo the modulus I just created. So really, I want to think of this as a method for solving modular equations. How did we read that? When I gave that symbol previously, I didn't use equals. I said something else. That was when I'm doing logic, congruence. Because I'm dealing with numbers here. So really, I don't want to think about these as solving equations in modulus. I want to talk about solving congruences. I want to solve for x. But I'm working in a different universe of numbers now. I'm working mod m. I'm working in integers. If you wanted to solve for x, if this was a regular equal sign and that wasn't there, how would you solve for x? I just divide by 2. But when I'm working in this universe, the number 3.5 doesn't work because I want to solve this in the integers, mod m. Oh, crud. I can't use 7/2. That's not an integer. That's a rational number. You said divide by 2. I want to think of this slightly differently. Instead of thinking of dividing, I'm going to think of multiplying. Because I know how to multiply in this universe. I know how to multiply in this universe. To go from here to here, what did I multiply by? And what's special about 1/2 is that 2 times 1/2 is equal to 1 in the integers, but in the rational numbers. I'm in integers over here. 2 times something can I find some number in the universe of integers where this holds true? Sometimes, if I'm lucky. Because if I think about it, I don't have to think about this as in all the integers. I really only have to think about the integers mod 9. Because I really only need to worry about the numbers between 0 and 8. I'm thinking about adding in this universe, which means I add and then take the mod by 8. I think about multiplying in this universe. I multiply the numbers, then I take the remainder, mod 8, mod 9. Use the number I wrote down. Really. So, I want to find a multiplicative inverse. Just like this is the multiplicative inverse of 2. I want to know, is there a multiplicative inverse for 2 in this universe? Well, let me start multiplying. What's 2 times 0? So that's 0 mod 9. How about 1? 3. That's a 2. 4. 2 times 3. 2 times 4. 2 times 5. Because 10 is 1 9 with 1 left over. That's the remainder. Son of a, I found an inverse. Wait a minute. I was trying to solve 2x congruent to 7. Right? And we just determined that multiplying on the left by 5 will cancel out that 2. If I multiply on the left by 5, what do I got to do on the right? But you just told me on this side, I'm going to get a 1. Because 5 times 2 mod 9 is 1. On the right, five times 7. Well, what's 35 mod 9? You own a calculator. Don't just stare at the screen. Try and do it in your head. I claim that's the right thing. What's 8 times 2? And 16 mod 9. My remainder mod 7 is remainder mod 9 is 7, just like I wanted. Now, I'm going to be the first person to admit there's a problem here. This one was rigged. Because if I ask you to do the same thing for the equation three x is congruent to 7, let's find our multiplicative inverse. What happens when you go to find your multiplicative inverse? We have to start multiplying things by 3 to see which one gives me a 1. Mod 9. Just write down the remainder mod 9 in each of these cases. 3 times 0. Good. 3 times 3. Wait a minute. 3 times 3. But that remainder is 3 times 6. 18. But the remainder is 3 times 1. 3 times 4. Mod 9. Remember, I'm working mod 9. 12. 12 is 1 9 with 3 left over. 3 times 7. Because it's 2 9s with 3 left over. My problem isn't it keeps repeating, because I only look at the numbers from 0 to 8. That's the only numbers that exist in Z9. We've gone through all of them. Which of them is the multiplicative inverse? None of them. Here's a problem. In the universe mod 9, Nothing times 3 ever equals 1. Ever. Why? Sick, nasty man. Well, that's a given, but that's not the reason here. The reason this doesn't work is because 3 times 3 is 0. That's the reason this is broken. Because this number just broke one of the big rules I learned in arithmetic. If you have two things and you multiply them together and you get 0, what does one of them have to be?
Yeah.
Well, what is going on right there? I have two things, neither of which are 0. I multiply them together, I get 0. Gosh. Let me change my modulus. I'm going to work mod 12. Here's my clock. I'll work mod 12. So let me see if I can find things that when I multiply them together, I get 0 mod 12. But neither number is 0. 2. 2 times something equals 12. Okay, so 2 times 6 is congruent to 0. What about 3? Well, 6 then works. What about 8? Hmm? 8 times 3 is 24. 24 is 2 12s with nothing left over. Wait a minute. 9. Is 36, which is 3 12s with nothing left over. I need to go through I need to go through multiples of 12. 12, 24, 36, 48. On the other hand, 1, 5, 7, and 11 are all have something right? Five times 5 is 25. That's one more than a multiple of 5, multiple of 12. 7 times 7 is 49, which is one more than multiple of 12. 11 times 11, 121, one more than a multiple of 12. Okay, wait a minute. We just divided up the numbers mod 12 into two groups. The ones that do have inverses and the ones that don't. Now I'm going to ask you what I think is a reasonable question based on what we just finished doing. What's the difference between those two groups? Oh, but I didn't know that in advance. I had to work that out the long way. What's another difference between these two groups that I could know in advance without having to start checking all these different multiplications?
The greatest common denominator is the first group is just one.
The greatest common divisor. That top group, they're all relatively prime 12. The bottom group isn't. You can only find a multiplicative inverse if the numbers are relatively prime. That's why 2 and 9 work, but 3 and 9 do. Greatest common divisor of 3 and 9 is 3. Greatest common divisor of 2 and 9 is 1. Why is this true? This is true because it's a huge result. Right? Wait a minute. I'm going to do a mod m on both sides. If I do a mod m on the left, what do I get? 1. Because 1 mod any number other than 1 is 1. And we know that m is bigger than 1. P times m is 0 mod m, because it's a multiple of m. That means this piece goes away. There's my multiplicative inverse right there. I just found the number. Which really means if I want to know what the inverse is, the fast way to do it is to do the base 2 coefficient. Which means I got to do the Euclidean algorithm, and then I got to do all the Euclidean algorithm stuff backwards. But it only works if the greatest common divisor is 1. Greatest common divisor is something else. I need another way to do this. So here's the problem. I can tell you what the greatest common divisor of these two numbers is. I can use my calculator. I can tell you right now what the greatest common divisor of these two is. Greatest common divisor is 1. Knowing that doesn't help me get S. Knowing the solution to the problem isn't enough. I have to do the work in the middle, figure out how to get S. All right. Walk through it with me. Give me the quotient remainder. Let's do the Euclidean algorithm. We've been doing an awful lot of quotient and remaindering.
You're in 54.
So 89 is some number of 54s with something left over. So now I put the 54 over here, and I put the 35 here. $35 on this side, 19 on this side. $19 here, $16 here. 16 and 3.
4 and 4.
Wow. You're dividing by 3. Your remainder can't be bigger than 3. Wait a minute. My next move is to put the 3 over here and the 1 here. That's going to give me a remainder of 0. So this is where I know I stop. My greatest common divisor is 1. Now I got to work this sucker backwards. I'm going to do all the rewriting right here. So I just rewritten all of those equations to get the remainders alone. And now you're going to start 1 equals. And you're going to keep using these from the bottom up until you get to 232s and 89s only. But the 3 was 19 minus 16. Don't forget that the 5 was out there. So that's 6 16s minus 5 19s. Wait a minute, 16's the remainder up here. 6 times 35 minus 19 minus 5 times 19. And so on. I want you to finish this out. When we come back on Monday, I need to know what the multiplicative inverse is. And then we'll see how we use it to solve it. I will see you all on Monday. If you came in late and still have homework for me, please bring it up. Otherwise, enjoy your weekend. Thank you. Thank you. You.